So today, what we did was discuss entropy, and we proved a few things. And now I want to, so we proved that the tail sigma algebra has some relationship to entropy. So we proved that T is trivial for almost surely trivial in the sense that it's not just the empty set in omega, but in the sense that all events have probability 0, 1, if and only if random walk entropy is 0. Okay? So all of these things come together. T comes from the space of the random walk. I mean, almost surely trivial. The almost surely part comes from the mu, right? So you have to put mu on both sides. Very big question. Very big question. Conjecture. One of my favorite open problems. I will repeat in different versions throughout the course. If u and nu are in SAG2, finite second moment and symmetric and adapted, then the entropy of mu is 0 if and only if the entropies will not be equal. This is definitely not true, but one of them will be 0 if and only if the other ones. So tail triviality does not change if you change between symmetric random walks with finite second moment. So this is,
There is no relation between mu and u.
no relation except for that they're on the same group and that they have finite second moment.
If there's the conjecture is that if there's one with 0 random walk entropy, all of them 0 random walk entropy when we talk about the stem random walk.
Yes. So it will be equivalent to the Liouville property, and we conjecture that the Liouville property is invariant, changing between random walks with finite second moment. Symmetric random walk.
Is it known if you take bigger, like SAG3 or something?
No, it's not known. It's not even known. So this is open even for u nu with finite support. Don't know anything about this. Even if you take, this is, okay, so even if you take nu to be epsilon mu plus 1 minus epsilon u prime, take some tiny perturbation of mu, something like that.
I don't know.
Okay, even if you take, even this is open. Like, mu is basically mu, but you add with probability epsilon, you add some delta S inverse also. Right? Take a new generator. Of course, if S is part of mu, then maybe it doesn't change. You just change the distribution. What it does depends exactly on the situation. But suppose just take a generator and change its distribution slightly. There's the weight of the probabilities on it. Even there, we have no idea. The harmonic functions completely change. You can change the value of the entropy if it's positive. You can change the value. These you can produce examples. But if it's 0, it shouldn't be able to change. I don't believe. Okay, so I mean, this is wide open. We have no idea on how to tackle this. This is central conjecture in the field in disguise, because we didn't talk about bounded harmonic functions, but I mean, it relates to it. Okay, so what I want to do is I want to talk about the relationship between entropy and bounded harmonic functions, at least part of the relationship. I won't go into everything because I want to get to Gromov's theorem. If we come back to bounded harmonic functions, we'll go into more depth. And in fact, we'll see today that it's not exactly bounded harmonic functions that we're going to be talking about, in fact. Okay. I'll see. And so I want to go back to the definition of entropy. So you remember when I motivated entropy, I showed you that there is some kind of penalization, there's some kind of score I can give, a score of bad points or something that money that I don't give you back, something like that, when you make a prediction about a probability measure, right? And this is the best score we can, this is the scoring system that encourages you to predict the best possible thing that, approximate the probability, real world situation. And that was the DKL, so the Kullback, Kullback-Leibler divergence of two probability measures, U and nu, on a discrete space. Okay, so on a discrete, countable. Right? Is defined to be d mu, two lines nu. I put two lines instead of a comma to remind you that this thing is not going to be symmetric. Okay, this is not going to be symmetric. And the way we defined it, or the way we, what we got there is that we sum over all possible x's in our space, whatever our space is, mu of x log mu of x divided by nu of x, where p log p over 0 is infinite for p greater than 0, and 0 log 0 divided by 0, 0. Okay, this is how we interpret everything. 0 divided by 0 is non-interpretable. But if you interpret it as a difference between two 0 log zeros, then it's okay. So this is actually a difference between two things. How we got it, remember. So this is called the Kullback-Leibler divergence. Exercise. We use the exercise, show that d mu nu is greater or equal to 0. I mean, what do you use for this? You should be able to guess, right? What do you need for such a statement? It's a Jensen's inequality, right? Just figure out the correct Jensen. And show that d mu nu is finite if and only if u is absolutely continuous with respect to nu. Absolutely continuous means every time nu is 0, mu is 0. Okay, but not the opposite. Mu could be 0 when nu is not 0. So this is the Kullback-Leibler divergence. Good. Another thing that we defined yesterday was the information. Definition, mutual information. Oh, no. So if x, y, big values in a certain space G, so these are random, not necessarily real valued random variables, but just countably valued random variables. And they're measurable.
About the first exercise about it's finite when it's absolutely continuous. U with respect to nu. That's like we want to prevent the explode over there, or
Well, you have a sum here.
yeah.
The sum of
I mean, this you're going over like countably many x's. So
you're only counting, you're right, you're only going on the x's for which this is a positive thing, right? Okay.
But this
And-
can't be too large.
And you want to say that this sum converges, is finite, if
It doesn't this condition only prevent me from getting like this infinity, but even as a sum of finite things, can it goes to infinity?
Maybe if you assume
No,
that the,
because-
sum is finite, maybe you can get converged.
oh, okay. You mean that this could grow? Yeah, you're right. Good, it's good. I'm thinking of finite spaces. You're right. Okay. Um, back in my notes, it's correct. So if these are measurable, okay, then we define the DKL between them. I'll probably usually say DKL. DKL is Kullback-Leibler divergence. Some books they write the little KL. There are different kinds. There's other kinds of divergences. It's a weird function. It's not a metric function. It's not. You can think about examples. So we just define this to be the divergence between the probability measure for X with respect to the probability measure for Y, right? Okay, that's how we define it. This gives a probability vector, this gives a probability vector, and you can define it. This is just so that I can talk about the random variables instead of
This is a random variable.
what?
It is a random object.
But it has a law. It is the distribution.
This is not a random object. This is just a vector. Run over all the little x's and you ask what is the probability that x equals x, right? So just it's the law of x. It's a law of x. And reminder, yesterday we defined something called information. So the information, mutual information. So this is called mutual information of x and y. That's just the name. And now I do put a comma because it is symmetric. And we defined it to be h of x plus h of y minus hxy. Okay, which is obviously a symmetric thing. But if you remember what the definition says, this is just the same as h of x minus h of x conditioned on y. And of course, you can reverse the roles of x and y because it's symmetric. Although in the second term, it's not obvious. The symmetry is not doesn't obviously pop out in the second term. But I mean, you see that it's symmetric. Okay. It's non-negative. This is always non-negative because this is bigger than this, or these two are bigger than that, right? Equal to 0 if and only if x and y are independent, right?
Intuitively, you have to think about it like if they're independent and they don't share any information.
Yeah. So one of them doesn't give you any information on the other. That's this is what is this? This is how much information y is giving you on x, right? Because this is how much more information you need to get x from y if you know y, and this is how much information you originally needed to get x from nothing. Difference is how much information y gave you about x. Okay, and it's symmetric. The amount of information y gives you about x is the amount of information x gives you about y. It's a miracle. No obvious reason that should be true, right? It's I mean, it doesn't. At least in my mind, I don't see obvious symmetry about that. It just comes out of the math.
What I wanted to say that when you phrase it like that, it doesn't sound symmetric.
Yeah, but it is. And even if you write it, it doesn't look symmetric, but the first term is symmetric. So, okay, so exercise. Maybe we do this one together. Exercise. So we can write the R of y. We have two random variables, x and y, in this situation. And we can write R of y is going to be all the y g. So that the probability is not zero. It's the range of y. Right? All the values y can get. Okay. This is, of course, a countable set, but don't know if it's everything. It's not necessarily everything. Okay. And we define this. And now I want to say for every y in R of y, we have a new random variable, which is x conditioned on y equals y. Right? This is function omega to g with law probability that this guy, so I'm just giving it a name, okay? Probability this guy is equal to x. What is it? It's exactly the probability that x is equal to x conditioned on y is equal to y. The fact that you have such a function is a theorem, but you can find such a function, okay? Or if you want, just define it to be in some other probability space. Okay, so this is a random variable with law. Okay, well, we can always define this maybe by extending the probability space. This is a conditional random variable, so we should think about that. Now, all of these things, they don't. Okay, so notice that mutual information. It's important that that the pair lives on the same space, right? For mutual information. I mean, you need them to live on the same space. I'm living in this extended space where I have all these things, and then I define. I mean, it really deals with the pair, so it talks about something how they work together, right? It's not just about one of them. And so the exercise is okay. This was just definition. So the exercise is that if I want to compute the mutual information between x and y, what I can do is I can average y, okay, and look at the DKL between, so let me write one term. I can take the expectation of the D between x conditioned on y with respect to x. Get it correctly, not get confused. Yeah. Okay, what does it say here? Now I have to make sure that I'm writing things correctly. There's an expectation here, so this has to be random. For this to be random, something inside has to be a function of omega. The only guy that I see here that's a function of omega is this. What value, what y equals little y, right? Because this thing is not a random variable, it's a random variable for different little y's. Okay, so I get different distributions. Okay, so if I want to interpret this, I'm averaging over y's. Okay, so if I want to properly write what this says, I'm averaging what? Yeah, so otherwise this would be zero, so I can put it in ry, okay? I mean, if it's zero, it just doesn't appear in the sum, so it's not important. And then I'm taking the DKL between x conditioned on y equals y, this distribution, with respect to this distribution. Right? This identity is the exercise. Let's see. I mean, basically, you just have to work everything here out, right, and see that it follows. Okay, so okay, so what is this equal to? Color for the proof. What is this equal to? So this equal to what? Summing over all the y's. Could write r y, it's not important. Probability that y is equal to y. Summing over, now, this guy, what do I need to do? I need to sum over all the x's in the world. It's enough to sum over the ones where this distribution is not zero, and when this is not zero, it's definitely x has to be in the range of x, right? Because the conditional doesn't give you more non-zero values, just less. Okay, so this will be in the range of x, and then I have probability that this guy is equal to x, which is the same as probability that this is conditional probability, right? That's the definition. And then I can take a log of the same measure here, divided by the measure for x at the same point. Right? This is how I define DK. Everybody agree? This is mu,
Run over all
this is
the-
nu, this is mu, this is mu, this is nu. I can run over all x, yes, but it doesn't give me anything new. So what I wrote is correct.
You need not to divide this by zero when, you don't.
Well, I said zero, log zero is zero. But this now and nothing is zero here. And no division by zero, I know. Okay?
But then this change the,
What?
because before you allowed zero and then you get infinity.
Yeah, but here you want.
No, but this is always when this is zero, this is zero.
It's continuous.
Okay? Could still get infinity if summing too many things. Now, what happens is that I bring this guy in here, right? So I get the double so now we sum over x and y. Okay. And then the right things. X, y is equal to y, right? And then we get, one time we get the log. Now I have to write this properly. So this is log of the product, the log of the intersection divided by the probability of y, right? So I get log of this. That's one of them. Okay? Then I get log. So now it's minus because they're in the denominator, right? So minus log of what? I have px is equal to x. And I have another term like this in the minus sign from the conditional. Log of y is equal to 1. Okay? Now, miracle happens. And what is this? So here, y is, I just sum over the y's, right? They go away. And I have sum over px, log px with a minus sign. So this is exactly plus hx. Same thing here. Here I sum over the x's. I get plus hy, right? Plus because there's minus sign here. Okay? And here, it's just going over a certain distribution, but without a minus sign. So this one is minus hxy, and so you exactly have the I. Just, okay. Lemma.
You just gave two equal things to two different names. That's what you did, so it doesn't surprise us that it's the same thing.
Surprises me.
No, we definitely, we
So it's kind of a way to describe every equality.
We
It's a non-trivial equality. You average some,
Yeah.
you define some quantity, the average of this quantity gives you a different quantity that you have to find. Of course, it's going to be equal at some point. I mean, if they're equal, then they are describing the same thing.
Why is this h of x? Like that?
What?
Why is this h of x? Because the run over all y.
This one?
Yeah.
So when I sum over all the y's, this disappears, and then I have sum over x, px, log px.
Oh, because the mistake of, okay, yes.
Lemma. Let xy be random variables, again, not necessarily let's write the g valued random variables, take values in g, and let f be any function from g. You can even do complex, but okay, any function, okay, that the expectation of f of x squared is finite, and the expectation of f of y squared is finite. And time will be a square is inside. Then I can look at f of x, okay? Yeah, I can look at f of x and I can take expectations. So this is indeed complex expectations. You have to be careful, but it's just really intuitive. You want to you do it for the real and imaginary parts, and then you just take sums. That's what complex integration means. And you can look at the difference between that and this. So these are both well-defined complex numbers because I've taken something in L2. Okay, so definitely it's in L1. And I can ask for the difference in absolute value of this thing. Okay, and this is going to be less than or equal than 2 times dxy times the sum of the second moments. This is just a scaling. Of course, if you multiply f by some constant, right, then it's impossible to get a uniform bound. So you need some kind of scaling on the right-hand side. And my feeling is that I forgot a square, of course, right? Because it should be homogeneous to multiplication by constants, such an inequality. Or put a square root on the other side, doesn't matter.
So and you can put either dxy or dyx if it should be true.
Everything else is symmetry. That's good. You could put the minimum in between dyx, dyx. This is what. This is important lemma. That I'm going to use in the lemma is this function x log x, right? Or c log c. So consider this function. I'm not going to write x's, I'm going to write r's. Okay? It's easier on in text to write x's. Okay, so r log r, this is a real valued function. I mean, you have to be careful around 0. Okay, let's define it continuously.
We prove a dilemma or we use it? We are using it.
Find this for r in 0, 1. Okay. What?
Are we proving dilemma?
Yes, this is proof of the lemma. Fundamental lemma, and then we have today we're going to prove the cool inequality. Yes, this was its name.
Cool.
What?
Will be the judge.
No, already in
I
plan.
think I remember when I was in St. Flo and Asaf Nachmias gave talks about circle packings, there was a lemma called the magical lemma or something like that.
Well, the reason this is called the cool inequality is because when I was giving talks about this, some people, I didn't want to refer to it, so I said this cool inequality, we're going to use it a few times. And then we kept saying the cool inequality. And then in a recent paper, well, a few years ago, Tom Hutchcroft and wrote in one of his papers that where they use this inequality. He said this is sometimes in certain circles, this is known as the cool inequality. And then that's it, now it's the cool inequality. And I'm promoting this name.
So for both inequality.
Well, cool both inequality. Well, I mean, it was independent, the inequality versions of it were independently proved by a few people. But we were kind of the first to notice the implications.
Cool.
Yeah, that's cool. So, okay. By the way, we're not doing any groups now. So what I'm doing is very, very general. That's part of the strength of this thing. Okay, so let's prove it. So what I want to define is this nice want to define is this nice quantity, Jx and y. This is going to be, or just call it J, okay? J, which is Jxy, is going to be the sum. Careful here, this is a very weird thing. This is going to be the sum Z of top. I'm going to put probability x equal to z minus probability y is equal to z, and I'm going to put a square on that, and I'm going to divide by the probability that x is equal to z plus the probability that y is equal to z. And for this, all I need the z's to be somewhere in the range where these two are not zero. So you can think about it, if both of them are zero, then the top will be also zero. So there's really, this is really only summing over the thing where one of them at least is not zero, right? And if one of them at least is not zero, then on the top, then we don't care about the top. I mean, it could be zero. Okay, so we're summing this thing. What I want you to notice is that we can tailor or expand this function. So what is the first derivative? Well, okay, you can compute two derivatives of this guy, okay? And inside the open interval 0, 1, okay? And what you get from the first two derivatives is that,
Not the J, the phi. Function.
yeah. So
R log R, not this.
so what is 3 prime of R?
So you spend it
So
around.
you get log R plus 1, right? Or R between, and then what is the second derivative of phi? This is just 1 over R. Okay? Now when you write, expand this around, so this is good for positive R's, right? And we can expand this around 1, okay? If we expand this around 1, we get that phi at 1 is 0, right? So we get that phi of R minus phi of 1, which is 0, is equal to first derivative at 1, right? Okay, yeah. First derivative at 1, so this is log R, log 1 plus 1 is a 1 times R, right?
Times R minus one.
R minus one plus, what else do we have?
R minus 1 to the power of minus
Uh,
minus R minus 1 to the power of 2 over 2. Wait,
plus 1/2 second derivative, okay, of
At one.
one, which is 1 times
R minus one square. Not R minus one, but for some point between R and one. What you want to do?
you write the Lagrange remainder, or
You want to remain?
why am I doing it this way? What I want to get is an inequality, so
לא, הוא פשוט העביר את הרפי של אחד, זה המקדם הראשון, הוא העביר אותו.
טיילור זה שפי של R שווה לפי של הנקודה של טוב.
זה נכון, זה אותו. אוקיי, אז זה R מינוס 1 ועוד חצי.
so what we get is half,
המקדם של השני זה 1, אז R מינוס 1
no, times R minus 1 squared,
ועוד.
right? Times 1 over some R star, right? That's second derivative at the point in between, not the opposite. That's what
you
you
write the Lagrange remainder.
Yeah, so I don't know who's remainder it is. I don't remember. I never read this. There's some point R between R and so depending whether
Yeah.
so
Between.
it should be R between. We're doing it for R between strictly smaller than 1, so it's between R and 1. Okay. Okay, so this is there exists something, but now R star is bigger. Okay, and this is everything is non-negative. So this thing, when R is bigger, this is completely confused now. I want to say that this is bigger or equal to R minus 1 plus R minus 1 squared divided by 2R plus 1. Is this correct? Probably could get something better. That's what I wanted to say.
Yes.
Right? So is it true? Good. That's all I want. Okay? So phi of R is bigger than this. Okay? For all R between 0 and 1. Good, good. Now I have what I want. So that's just so I mean, basically, you could also prove this inequality, you know, using other like, you know, you could take the difference between the two things, show what they're at the endpoints, and then take derivatives to show that it never gets bigger than 0. But but it's basically just Taylor expansion. So this implies that what? That if we take J, okay, we take J. One thing, we can assume, without loss of generality, we're going to assume that Rx is contained in Ry. Okay? So what this means is that whenever Y cannot get whenever that any Z that Y gets with probability 0, also X gets with probability 0. Okay?
It's like a large assumption.
Well, so why can I assume it? What am I trying to prove? I'm trying to prove that this is less than or equal to D times this. What happens if X is not mutually, is not absolutely continuous with respect to Y? This thing is infinite, right? I'll just have an infinity in one of the summons for this term, DKL, okay? And so if I have an infinity here, there's nothing to prove. Without loss of generality, I'm assuming that this is finite, which implies that that happens. Okay? Otherwise, I don't need to prove it. Okay? Good. So if I assume this, then I can rewrite J. Rewrite J as the following. I sum over all the Z in Ry, right? No need to sum anything, right? and then I divide everything here by py equals z, okay? So what do I get? I get the following thing. I get, let's use the notation, rho of z is going to be p x equals z divided by p y equals z, okay? Just so that it'll be easier to, okay, now I can write. I can always write this, right? Because we assumed absolute, that was the point of assuming absolute continuity. And then we're going to rewrite J. So J is the following. So it's the sum of, so it's rho of z minus 1 squared, but then this I divided by py, right? I divided by py, so I have to multiply by py squared. Okay? Okay, so I get, but I also want to divide the denominator by 1 py. So here it's rho of z plus 1, and then I only need to multiply by one of the py's, right? So now I get py equals z here. Okay, agreed? And this is the same computation. Okay. And now you see this has a nice form. This is r minus 1 squared divided by r plus 1 for a number between 0 and 1. I can use that formula, which gives me an upper bound on this term, but which is phi of rho of z plus or minus, sorry, plus a linear term, right? Plus a linear term, okay? So it's plus 1 minus rho of z.
We don't know rho of z is always less than 1.
Yes.
No, but this inequality, so this inequality was true for any r bigger than 0.
No, but you use the Taylor expansion and use.
Yeah, but I again, this is between r and 1, okay? And I upper bounded it by r plus 1. It's either smaller than r or smaller than 1.
So I say it's between r and 1, but you allow now r to be bigger than 1. Or the other direction.
Yes, so all I'm saying is that this guy is less than r plus 1.
Yes.
It's in fact less than the maximum between them. Okay, yeah, you're right. I needed, actually, like, yeah, that was a good comment. I need this inequality for every r bigger than 0. Okay, all I'm using is the rho of z. Well, okay, when rho of z is 0, so I get here 1.
Get 1, here, there you get.
So wait,
Is it 0?
I think what happens at 0? So at 0, this is 0. Yeah, I do have the inequality at 0 because when r is 0, this is 1, this is 1, this is a half. Okay, this is minus 1. So when r is 0, this is 0 and this is minus a half. Okay, keep it. That's the. We could have taken care of the answer. Okay, but so this is what we get. Okay, are we good now? Okay, now what do? Well, we start being careful about things, opening up the sums again, right?
Are we using a 2-factor?
We are missing a 2-factor, right? So it's 2 times everything. So that's where the 2 comes from, actually. In fact, this 2 is important for a consequence of this. So a consequence of this is something called Pinsker's inequality, which I will not teach at the moment. But Pinsker's inequality, there's a lot of research going into the optimized constant here. And if I could get a better two, the better constant than a two here, then I would be able to get the actual optimal constant for Pinsker's inequality. But for me, it's not so important, just some constant.
Should we divide the linear part by two?
We multiply this whole inequality by two, so this gets divided, this gets, it's just two. That two, right? Because we had r minus 1 squared over r plus 1, which is what we had, rho, right? Rho is r. So we have this, let's open up the sum. So we get 2 times, now you see, you start to see at least where you would think the DKL comes up, right? Because you see the phi, right? So you get the probability that y is equal to z. You get, now let's write what phi is. Phi is rho log. X is equal to z divided by probability y is equal to z. This is exactly DKL, right? So the first term here, this is exactly dxy. Great. Okay. Plus 2 times summing for all the z r y. What do I need to get here? Now I need to get some 0, right? Well, okay. This is just bounding j. So sum z in ry, okay? Probability that y equal to z, right? I'm doing this guy, right? So 1, probability y is equal to z times 1 is just 1, okay? Just this, minus 2 times sum z in ry. Probability y is equal to z times rho of z, which is probability x is equal to z divided by probability y is equal to z. These guys cancel. This sum is 1. This sum is 1. The 2's cancel. So this whole thing is 0. So as a consequence, going back to the start of the proof, let's leave this on the board, right? Going back to the start of the proof, what I've just showed you is that j is always less than or equal than 2 times dxy. Okay. Well, let's see how we can use that for a general function. General function, the definition of j. For general function, f, right? So now I have a general function f in L2, whatever, right? L2 of the proper spaces. And I want to bound this thing, right? So I'm going to write what is the expectation f of x minus the expectation f of y in absolute value. And we can leave a square. Okay. What is this? Well, this is equal to sum over z, probability that x is equal to z times f of z, right? Minus probability that y is equal to z times f of z. So I put them together in the same sum and I write here f of z and everything converges absolutely. So I'm not in, don't have a problem. Right? Putting the two sums together because they converge absolutely. Okay. You see that if I didn't assume that the squared moments converge, there's nothing to prove either. I mean, the right-hand side says infinity. So, and in fact, the left-hand side may not even be defined. So assuming this was not a big assumption. Okay. Good. Sorry, yeah, so let's not do the square. Let's not do this square. This is, okay, let's keep it. Well, I started square. We'll keep it. Now what I do is I pull in the absolute value. I pull in the absolute value. Okay, so this we can actually do quickly on the board using this magic. I can put an absolute value here and turning this into an inequality. That's still fine, right? And I can put an absolute value on the f as well. and everything outside is squared. Okay, agreed? Now what else can I do? Oh, this looks nice. This looks nice, right? This almost looks like what? J. I can do this. Oh, by the way, what happens when Z, before I do this, what happens when Z is not in the range of 1? I get 0, right? I can restrict myself to Z in the range of 1. Okay? And then I can divide by probability X equal to Z plus probability Y is equal to Z, which is non-zero, and multiply by this square root. So multiply this guy times square root X equals Z plus Y equals Z. Okay, this is the square root, and then everything is squared. Okay, so I didn't change anything, but now what do? Cauchy-Schwarz, of course, right? So I square this guy, what do I get? Sum over all z's of this squared is just j. Now this is Cauchy-Schwarz, and I get j times, what do I get there? The sum of this thing squared, right? And what is the sum of this thing squared? The sum of all z, and now take more z's because the other one will just give me zeros. Right?
The sum of
Yeah.
L2 norms.
Yeah. So I get f of z squared, right? Times probability x equals z plus probability y equals z. But this is exactly the sum of the L2 norms. Not the L2 norms. This is sum of the second moments. Okay? Exactly. When you split the sum into two parts, you know they both converge, so you can split it into two parts. First part is the one for x, the second one is the one for y. Okay? You get exactly this. J was bounded by 2b, and you get exactly this. Okay? And this again, it's really just a computation. The only trick was understanding that little what's it called? Taylor expansion, right? And in fact, it was very important that we had the r plus 1 on the bottom there, because it was what bounded the maximum. But somehow, if we didn't have a linear term in r, if we had the maximum between r and 1, right? This would translate into having into defining j differently, where on the bottom of j, I would have the maximum between rho and 1, right? Which would be very, which would probably say that I put the maximum between x and y here, right? Probabilities. And that's something not natural to compute. I mean, not natural to use in a computation. I don't see how I could have, because it would have given me a tighter bound, right? It would have given me a better, smaller j. If I had this j prime, which would put the maximum here between these two instead of their sum, and would have given me the best bound, and the whole thing would still be okay. But I don't know how I would have bounded. So this term would turn. So these would turn into square roots with the maximum, and so I would have the sum over z, f of z squared, maximum between these two. And that's not an expectation. So it's not clear to me what that would even say. Okay. So actually, sometimes. And this is pretty tight, up to that constant 2, this is tight, okay? Because it implies Pinker's inequality, which is tight up to changing that constant. Okay, so let's take a 10-minute break, and then I prove the Cool inequality, okay? The consequence before we do the Cool inequality is the following. Corollary. So I want to use later, so let me do corollary. A, B, p-valued variables. I'm using A, B on purpose because I want to use X and Y later for something else. And one of them will be A, one of them will be B, so we have to be careful. Okay, so and I have to not get confused. Okay, and F is such that now I only need this second moment. It's not X, it's A. Okay. Then we can bound the following. We can look at the expectation of F of A conditioned on B. This is random, right? This is random, but it converges because F of A in absolute value converges, so it's right. So these are always integrable, right?
Double notation to write A and B for random variables.
Well, then you're going to get confused later when I use X for something else for the random.
These are sets.
Well, you're going to have to expand your horizons a bit. No, I don't agree. They can also be random variables, okay? And then I subtract from this its expectation, right? So what's the expectation of this guy? This guy, right? Okay. And then I take absolute value. And then I take expectation over what? The randomness of this guy, right? Because this whole thing was random. And then I take square. It would be much nicer if the square was inside, because then it would just be the variance, right? But it's not. We'll give a nicer inequality. And this is less than or equal to 4 times. What is 4? 4 is 2 squared. We had 2 before, now we have 2 squared. Okay? Well, actually not 2 squared, it's 2 times 2. So one of the 2's comes from before, and the other 2 comes from and it's just equal to then 4 times, I'm going to write what this is, 4 times information between not X and Y, but rather A and B, times the variance of F of A, which is a finite number because I assumed it has second moment. Okay, that's all. Okay, so this is a corollary from the previous theorem.
These inequalities often pretty random, but I guess they have something important.
What?
These inequalities have more importance, right, than what we see.
And what?
Than what we see here. Will we see the importance of this?
Well, hopefully soon you'll see one application of this school inequality and gives. First of all, this is, I mean, look, this is relating some kind of measure, L1 measure, to an L2 measure using the information, using entropy. So that's already an interesting quantity. It's for any function. The entropy relates L1 to L2. Okay? It's kind of a, this is, if you know some analysis, this is a kind of log subolive type inequality. Okay, you have these inequalities in analysis which relate L1 to L2, and Nash inequality, different type inequalities. One of those inequalities. So it's relating. I mean, this is not exactly an L1. Well, it is an L1, right? So it's relating the L1 norm in a certain sense to the standard deviation. Okay, keep in the same units. Again, everything is homogeneous. You multiply by a constant, you should get it on the same side. Otherwise, you have the wrong inequality, right? Okay, so proof. So how do we do this? Yeah. Indeed, how do we do it? Well, so what is this? So we start with a square, okay, and we want to write what goes on inside this. Okay, first of all, let's assume without loss of generality. So without loss of generality, the expectation of FA is 0. Why can I assume this? Why can I assume without loss of generality that FA has zero expectation?
The variance.
Because if I take f instead of the function f, I shift it by a constant, by this constant,
The variance doesn't change.
then the variance doesn't change. And I shift this by a constant and this by a constant, the constants cancel. This is it. The two sides are invariant to not only multiplying by a constant, but by shifting by a constant. I can shift f to be zero expectation, and in fact, I could shift it to be variance 1, right? Or second moment 1 as well, but maybe I don't need that. Okay. Now, we're going to use the previous proposition. I'm going to look at the expectation of f of a conditioned on b equals little b. So take some b in the range of b. Okay, right? This, you can take the expectation of this guy. Okay, minus the expectation of this guy. Right? Now, what the previous thing said was that this squared is less than or equal to 2 times doing x as x. Should have just done x and y and have you make the next time the leap of changing x to something else, different x. So this is dA conditioned on b equals b with respect to a. Right? This is what we said, times the sum of the second moments.
You're fixing the B and B because this is a random object, right? You have to.
Yeah, and now I fixed little b. I fixed little b, okay? And that's just one distribution, another distribution. So this is what previously, this whole thing was my previous x, and this is my previous y.
And why do we do the difference
We're
square?
missing expectation, right?
No, the previous lemma said, if you take expectation of f of x minus expectation of f of y, and you square it, then it's bounded by dxy, 2 times dxy, times the sum of the variances, right? The sum of the second moments, right? So the sum of expectation of f of a conditioned on b equals b is squared, right? This just tells you what the expectation is. It doesn't tell you what's inside f. Of course, you're plugging a into f, the value of a into f, but you're plugging it on a different measure. That's what's this plus this. Okay? Okay, that was the previous, this was the lemma. That was the lemma set. Now, I can multiply everything. Yeah. So instead of doing a square here, what I really need to do is an absolute value, because you see now I need to compute the expectation of the difference in absolute value. Now that the square is outside. Okay, so the difference in absolute value is less than the square root of this whole thing. Good. Now I multiply by probability b equals b and sum, right? So I take this and I do this. Okay, on both sides, right? It preserves the inequality. And what I get on the left-hand side is the expectation of the difference in absolute values.
Multiply both sides by.
Now we take
I just average this over little b.
So you multiply by this.
I multiplied by probabilities and then summed over all the little b's. So I averaged it. So it's just taking the expectation of a little b. Okay? And this is less than or equal to averaging this guy. So I have an average of a square root times a square root. What can I do with that? Cauchy-Schwarz. So square root 2 comes outside, right? Square root 2 comes outside. So this is additional Cauchy-Schwarz. Then I have sum over b of probability b equals b, b of a condition on b equals b with respect to a, times sum over b equals, right, because it's the sum of this squared, okay? Oh, and I need a square root on everything because it was Cauchy-Schwarz, right? So square root of everything. Okay?
Wait, over there, did you mean to write the condition expectation or is it supposed to be f of a condition?
Here,
Yes.
it's
No,
f of a.
on the left hand side. In the corollary itself. Wrote f of a.
Well, it's the same thing,
Oh, it's the same thing.
right? I mean, what does it mean? What does it mean when what is this? This, okay, this whole thing, I mean, this you can think of as zero. I mean, this is zero, right? So it's just a constant. What is this thing? It's summing over all little b's, probability that big B is equal to little b, times the expectation of under this measure. So this is this, I mean, the averages are this thing, okay? Yeah, actually, this is the correct way to write it because this is just the expectation fa conditioned on b equals b, right? Indicator that b is equal to b. It's a random object, right? Sum over all b, right? So, and how do you average, and this minus that, whatever, minus constant, put everything in absolute values, how do you average it? Well, you go over all the b, probability that b is equal to b, and when big B is equal to b, then you just get this one. Okay, for every different, so, and it's the same, okay? Then we have this, square root 2, we did a Cauchy-Schwarz, we get the sum of the square root, this square root squared, which is sum times this, and then we have sum over b and rb, probability that b equals b. What? This one's, the square root of d squared is just d. This square root is the Cauchy-Schwarz square root. And I have sum times square root squared. So the square root becomes nothing, right? So just sum times d. And then sum times this guy in the square root squared, right? So you don't see it?
I will make it later.
This is square root here, and this is square root here. Now I average these over little b. Okay? Then I do a Cauchy-Schwarz. Instead of averaging those over little b, I get square root of the average of this squared, but what is this squared? It's just this. Okay? Times the average of this squared, which is removing this square root. Okay? So I get these two things. And this square root comes from the Cauchy-Schwarz. And so sum b, probability b equals b, and then I have this plus this. So I have this. Plus this. Well, okay, this doesn't have a b in it, so I can just write this. Okay? This is it. Okay? But what is this? What is this sum? This is the expectation of the conditional thing, right? And you're averaging over the b. So you get the second moment of f. You get another 2, you see? Okay?
Okay.
Yeah, I mean, okay, well, we should write it this way. This is the expectation of fa squared conditioned on b, all of this in expectation. That's what it is.
That's just the expectation.
And that's just the expectation of FA squared, okay? That's what's written here. So you see you get that. So you get 2 times, but it's in the square root. So here we get a 2 because it's 2 times 2, right? So this 2 came from the previous lemma, and the new 2 comes, so the constant you get from the previous lemma is multiplied by 2. That's what you get. Okay. And then you have square root. What is the average of the DKLs? That's what we said before. This is the I, right? So this is I, AB. And here it's square root. And we already did the 2 of the second moment. Second moment is the variance because we assume without also generality that F had mean 0, right? Okay. Just computation again.
To come out without the square root.
There's 1, 2 here, which was the constant we had from the previous lemma. And then we get another 2 from the 2 second moments. And everything is in square root, so we get square root 2 times square root 2 is 2. And that's why it becomes a 4 here. So this 4 is actually equal to 2 times C, where C is the constant from the lemma.
This is what people are trying to make better.
Propinsko's inequality, yes. But
Who is the best we can do right now?
this method only gives 2, and I mean, I have no interest in improving this method. Don't see any use for it. If the truth was 1, then it would be maybe interesting. But since there is some weird constant that you cannot beat, then that's a different kind of area of research, if I mean research.
And again, how did we get the second part of that? Like the expectation of f of a squared?
This is this. So averaging this over B is not giving me anything.
And the left side.
This is the average, is just conditional expectation if I average over.
And
Again, you have to interpret what this says.
no, but where is it? Yeah, or do we think?
This average
Yeah.
is this.
Yeah.
Then plus this. But this is the same as this, so I have twice this. So the 2 came out and I had this. Okay, now, so erasing this, now I do the cool inequality. Cool inequality. Actually didn't use anything about random walks or anything, so I want to stress that I didn't use anything about symmetric, adapted, anything. So let mu be a probability measure on a group G. First of all, already this inequality is useful. I mean, it's kind of related, again, as I said, L1, well, 2. Let and assume that mu has finite entropy. Otherwise, we cannot write anything. Everything here is. So other things will not be finite. Okay, entropy of mu is finite. So one step of the random walk is finite. But I didn't assume symmetry. I didn't assume moments. I didn't assume anything. I will assume functions which have to do. So you will have to have moments if you want the following to be true. Let H be a new harmonic function this already gives you restrictions on mu because you know, the larger the tail of mu is, the less harmonic functions you can take because something has to converge absolutely, right? And we're not only assuming that it converges absolutely, but rather the harmonic function such that the variance of, so h of xt squared has finite expectation for every t, where xt is a mu random walk. Just multiplied mu are the elements, and you're assuming that no matter how many times you multiply, you still have a finite second moment. For example, if H is bounded, definitely true, okay? But you can imagine that the random walk, for example, if you started with a random walk with finite support, the random walk doesn't go too far in the group, and you have a function which doesn't grow too quickly. So this converges, right?
To repeat the last sentence.
Yeah, the last sentence was in fact wrong. I mean, uninformative. If mu has finite support, then xt is in a bounded set for every specific t. I didn't say that this was uniformly bounded. All I said was that it's finite for every t. Okay, so as long as, but even if you had infinite support, you just need the function not to grow too quickly compared to the tail of mu, right? So that these sums, the bigger t is, the more elements you're going to have to take into account because you're multiplying more and more things of the group. So typically, you need to somehow restrict the growth of h to work nicely with the tails of mu. The tails should decay faster than the function grows somehow.
Stronger than asking for absolute integrability, uniform integrability of the.
Yeah. This is second moment, so it's definitely uniformly integrable, right? Any 1 plus epsilon moment. No, but I did, sorry. I didn't say supermum over t. Uniform integrability, when you put the one of a supermum over t, 1 plus epsilon is finite. That's not, this is not.
Grows to infinity.
This can grow like t to the, this grows like e to the t, maybe, and could be. I didn't restrict in any way. Okay, so for any harmonic function, as long as things make sense, then this is the consequence, okay? You can look at h of x1. We're going to do this for any starting point in the group. You can look at h of x1, and you can ask, how does it vary from h of x0? You can take absolute values. You can measure the expectation of this, starting from x. So no matter what x you start from, you can do this. Okay? This is how this thing varies. Then the Coulomb inequality says this is, well, let's put a square here just to make things nicer. This is less than or equal to 4. This 4 is that 4. Okay? Times the variance starting at x, h of xt. Now, which t is this? Any t. This is the strength of this thing. I need t. Let's see, I have one. Any t. So on this side I have t, on that side I don't have a t. Okay? Times h of xt minus h of xt minus 1. But this sequence, remember what this converges to? The decreasing sequence converging to the random walk entropy.
H G mu, right?
Yeah. Okay? So there's an interplay between the variance, random walk entropy, and this. But this is a finitary inequality. It just looks at a fixed starting point, fixed t, no limiting procedure at the moment.
Wait, but can you take because the left hand side is not dependent on t and the right hand side dependent on t. Can you take the limit and then?
Yes, you can.
Then you mark out that
theorem?
then you will get only constant harmonic functions when it's 0.
We'll soon see the consequence of that for bounded harmonic function. But I didn't restrict H to be bounded. So maybe this can grow. It's a quantification of this. It's a finitary statement. It says things about finite things, not limited, not limits. So it gives you a quantification of the entropic criterion.
Well, one side is dependent on t and the other doesn't.
Yeah. Okay, so proof. How do we prove this inequality? Well, we define the correct function, right? So we fix x, t, okay? right? Because we're proving for every x and every t. And we define f of, how do we define f? Or we define it to be, what do I need it to be? So I want to use the previous one. Okay, so I have to be careful. So what I'm going to use is that yeah, I want the variance. I want, I guess, oh, I already have the variance in that statement.
You want.
Yeah, no, fine.
XP and B to be minus one.
Yeah, I don't need, so I just use h. Okay, I use the previous lemma with h instead of f. Okay, so just be careful, but in a second. So from the corollary, what it tells me is the following, is that when I look at expectation, starting from x, of h of, so what do I want? x1 minus h of x0. This is an absolute value. Okay, this is the left-hand side. Okay, did I put squares there? Yeah, I put squares there. Okay, we'll do it without squares. What is this equal to? Well, here I have this. Now inside, h is harmonic function. Specifically, h of the random walk is a martingale. Specifically, I can take expectations, right? Expectations at a certain time are equal to the expectation at time 0. But not only that, conditional expectations are equal, right? Martingale conditional expectation is equal to wherever time you conditioned on. So for any t, what is h of x1? It's the conditional expectation of h at time t conditioned on x1 minus h of x0 is just the expectation of h of xt.
Why is this corollary?
What?
With,
No,
By the corollary.
by the corollary.
Oh, okay.
I'm going to use the corollary in a minute. Okay? So first of all, I just write this. This, you see where the t comes in. The t comes in from the fact that I can take expectations at time t. Now this is in the form, this is exactly in the form of the previous corollary, right? Where this guy is A, that's why I didn't want to write X and Y. This guy is A, and this guy is B, right? Okay? And so, previous corollary tells me that this is less than or equal to, this is by the corollary, okay? This is less than or equal to.
Again, why can you take the condition expectation on x1 and
Okay, what is the expectation of h at xt? It's just h, it's just the expectation of, it's just h at x0. Okay, I put an x here.
that is
Okay, what is the expectation of h of xt conditioned on x1? Martingale tells you this is just h of x1. That's what the martingale tells you. Okay, so this is h of x1, this is h of x0. Okay. They have absolute values, same thing as that.
Wait, so you know from the martingale property that conditional expectation of xt minus of h of xt by xt minus 1 is
We just
xt minus 1
tower-
a couple of
Yeah, it's a tower, it's a tower, yeah.
Oh,
We said that at some point, but if you condition on previous guys, you get whatever you condition them in the first, the smallest. Okay. So this is, so by the corollary, this is less than or equal to. I didn't put the squares, I have to do a square root. So I get a 2, I get a square root of I of xt, this is my A, and x1, this is my B. Right? I have to be careful here that I'm doing the correct things. This is I is A and B. Right? And I have a square root of the variance of my function at A. Correct? That's what the corollary says. I used A is xt and B is x1. Just computed the left-hand side, and now we have to compute the right-hand side. So we have everything in place, right? I mean, up to taking squares of everything. We have everything in place, except for one object here, which we still haven't figured out, which is what is I of xt x1, right? This should be equal to this guy. That's all I need to show. Okay?
It feels like the information that xt and x1 share should be the same
So
information.
this is the group property. We already saw this yesterday. Xt x1, I'm going to do it here in the middle just to keep everything on the same board. Okay? What is this?
Yeah.
This is h of x1 plus h. Sorry. This is h of. We can do whichever one we want, and we actually want to condition on x1. It's easier to condition on what happened in the past. So it's h of xt minus h of xt conditioned on x1. But remember, what's this? This is h of xt minus 1 because we can bijectively go from random walk started at x0 to random walk started at x1 and multiply by this, right? So it's the same entropy, not same distribution, but same entropy as xt minus 1. So this is corollary. That was the end of the proof. Right?
We prove the code.
This proves the code inequality. Very good. Cool is a nice word because it's both English, French, and Hebrew all together. Probably a few more. Okay, so corollary, or sorry, exercise really follows immediately from this. Right? So recall, giving you an exercise, recall that G mu is mu v. Did we ever mention this? We never mentioned it?
What?
Up to now, we did not. So it's not an exercise, it's a definition.
Exercise plus definition.
Definition. G mu
Definition plus that too.
is called mu v. Of course, mu probability measure on G, right? I didn't assume symmetric, I didn't assume anything. I didn't even assume finite entropy. Just mu is a measure on G. It's called Liouville if every bounded U harmonic function is constant. It would be reminiscent of the classic theorem called Liouville's theorem, which was actually proved by Cauchy.
Just like the Will just went around looking for bounded things and trying to prove that they're.
Well, and in fact, Cauchy's the Liouville's theorem is stronger than that. It's a deferred discussion for another day. Specific case of Liouville's theorem, which Cauchy proved, is that if you have a bounded harmonic function on Rn, then in the sense that Laplacian, which is the sum of the second derivatives, is 0 everywhere, and it's bounded, two conditions, right? Then it's actually a constant. Okay?
But it's not enough to be bounded on Zn, for example. Not all mu harmonic function.
Oh, on Z then it's
Then-
on Z then it's true, but we haven't proved it yet.
Oh, it's true for
It is true, yes.
For again.
Yes. Yes. For every random walk, for every whatever you want. But on Rn, there is a natural random walk, which comes from the natural Laplacian, whatever that means. Okay, it's bounded in motion, what it is. And because of continuous space, you don't have too many options. Okay? All martingales are bounded in motion in a certain sense. You have to figure out what that means. But it's up to a time change, and time changes doesn't, harmonicity doesn't get, so that's why you like really have one Laplacian in a certain way. There are other, what's called second order differential operators and things like that that you can discuss, and I don't know anything about them. But if you take the Laplacian, it's just the sum of the second derivatives, right? That doesn't have anything to do with a probability measure. But when you go to groups, to discrete groups, then you have different probability measures. So you can start discussing when you say Zn, what do you mean? So here we see there's mu is Liouville if every boundary harmonic function is constant. Now, I gave you the conjecture before, which, I mean, implicitly, maybe you don't see it yet, but the conjecture is that Liouville property is a group property in the sense that if you go between measures with finite second moment and symmetric, then it's preserved. But, we don't know that, so we cannot define it. Okay, so this is definition. Exercise. Now I can do an exercise. Okay. G mu. So now we need finite entropy. So we assume. Okay, this is finite. I'm not assuming any symmetry or adaptiveness or anything. Just this is finite. Remember, this was all the Coulomb inequality was just true for general finite entropy. Right? Okay.
Or did we use the assumption that it's bounded?
Which is bounded?
The h of xt is bounded for every t.
This
The variance.
convergence? Yeah, I mean the previous corollary and lemma were only true if you had finite second moment. Remember? So in order to even write this inequality, okay, if you want even this conditional expectation, I need to somehow know it's well defined. So but if the second moment was infinite, then this up to the translation would be infinite, and so there would be nothing to prove actually.
Yeah. So
it's actually true without this, but there's no it's an uninformative. So assuming that doesn't really restrict you. What restricts you is actually this. That's the only restriction, but it's a very mild restriction. Finite entropy moment. I mean, we barely know how to say anything. And that's a completely new world. Infinite entropy. Yeah, Kalmanovich likes this stuff, but I just tried to talk about him, and basically there were no results. I mean, we don't really know actually, and basically anything can happen also. That's there are lots of maybe there are a few negative results actually. There are no like positives. And you want to show the following. So the exercise, if you have finite entropy, you're in the nice, mildly nice world, then you want to show that G mu is Liouville. If and only if. Okay? If and only if. Let me go up here.
It really depends on the view.
You cannot show this because I didn't teach you the entropic criteria.
why? No, maybe I know. If the entropy is random walk entropy is 0.
So that the random walk entropy is 0. Okay? If and only if. Now it's a theorem that random walk entropy is 0 if and only if G mu is Liouville. But we didn't prove that theorem yet. But this gives you one direction. You'll see in a minute that this gives you one direction. Okay, so H G mu, if and only if what? If and only if for any H, which is new harmonic, and such that the supremum over all T of the variance H of xt. This is variance starting from the origin. I don't just need that, okay? Variance of H of xt. Supremum is bounded, so this is uniformly bounded variances. For example, if H is a bounded function, right? That's true. But you could a priori imagine that you have a function for which this holds, but it's not a bounded function, right? There could be areas in the group where the function gets bigger and bigger, but the random walk kind of has a hard time reaching those areas. It wants to go in different other areas. You can imagine that that's the case. So supremum of the variance is bounded. So for any such h, h is constant. Right, so this is an if and only if. Every such h is constant, the random walk entropy is going to be 0. Okay, but if the random walk entropy is 0, then every such h is constant. Now, what does this tell you? For example, if the random walk entropy is 0, so we already saw. So by the exercise, I'm not solving the exercise, but I'm just saying what the consequence is. So h g mu equals 0 implies what? Implies Louis. The other direction, you have to be careful with. The other direction we still have to talk about, but this already implies it. I mean, you already say it immediately from the thing, right? Because take a bounded harmonic function, right? So the variance is bounded, uniformly bounded, right? Just by the whatever square of the bound of the function or something like that, right? So this is just a bound. This is bounded by some number, but this is converging to 0 as t goes to infinity. So Gauss said take t to infinity, right? I mean, of course. And so this, right, for any x, this thing becomes, or even x equals 1. This is always 0, right? So what does it mean? It means that h of x1 is almost surely equal to h of x0, starting from 1. So if mu is adapted, it means that any guy in the support of mu has the same value as the origin. But now you can start playing around by shifting the function, and it tells you that all, right, because this is true for any function, so any shift of h is also true. So you get that for any point, if you shifted it, right, then you could put that at the origin, right, because the shift of h is also a bounded harmonic function. So we get Liouville. So think about that. I mean, it's very easy. So this is half the criteria. The truth is that this is an if and only if. Okay? The truth is it's if and only. But in order to prove the other direction, we need to go through something called an invariant signal. Okay. So yeah, and finish.